We certainly encounter a lot of them, especially if you live in actually almost any area of the country, but if you live in a major urban area, you can't help but deal with what you don't think of as bridges, but they are in fact bridges, and they have all the same problems with bridges that might be spanning a river or a corner of a lake, or like the new Hoover Dam Bridge. Anybody ever been over the new Hoover Dam Bridge? It's quite a bridge, huh? I haven't been over it. I've driven by it in Anderson, but it's amazing. And I think that's an example of one of the last bullet here, which says, in addition to being durable, that bridges can be aesthetically pleasing. Some examples of bridges that you may or may not be familiar with. Okay. So what is a bridge? Well, clearly a bridge is a structure. I'm not going to spend a lot of time on individual slides, but a bridge is a structure to span something. Maybe I'm not sure what's going on. I'm going to get out of the way of that moving lumber. Anyway, so we have to span some distance. A bridge has to carry some weight, right? And it has to allow for the passage of those people, the cargo, whatever, over whatever the obstacle is. More than 500,000 bridges here in the U.S. And as we all know, many of them are in very poor repair at this point. A couple of years ago, there was a bridge over the interstate in Minneapolis that collapsed, mostly due to deferred maintenance and weather-related problems. But what we're going to do is we're going to talk a little bit about how bridges work. Why are some bridges straight, some are curved, some are arched, some look very flat, and what are the engineering considerations that go into designing and building bridges? Lots of problems in building bridges. I mean, what's its function? Is it just to carry foot traffic? Is it to carry heavy loads? What kind of terrain are you covering? What materials do you have available to build it? And how much money do you have to build it? Typically, a bridge and the kind of bridges you're going to build are going to be supported at each end. Although we see lots of bridges that have intervening support, certainly virtually all of the freeway bridges that we encounter and many of the overpasses have multiple supports, which makes some of the problems easier. But we have to consider all the weight, and we have to design the bridge in a way that that weight is transferred from the middle of the bridge to the supporting ends. Now here's
this thing.
You gotta operate that from there.
Okay, this is, if you have to use the file, then you can actually
select the forces. Is it working on your iPad? Ah.
So at least you can use this to explain to the kids in various aspects.
Is it working?
No.
Yeah, select one. No, it doesn't.
Do you have a sheet of paper?
No.
The other way of explaining this was the structural engineer who worked on use this to explain. What we're talking about is compression, tension, and shear, and torsion. We go squeezing, stretching, bending, sliding. Squeezing is compression, stretching is tension. Bending is bending, sliding is what's called shear, we call shear. It's one of the things we do is to teach the kids the terms we use, okay? And twisting, that's torsion. A sheet of paper, if you hold it, that's tension, it's strong. If you push on it, it has strength, that's compression. If you bend it, there's no strength that way. And if you twist it, that's torsion. There's no strength that way. And this becomes important, as you're going to see in a moment, because when we're building bridges, what we're trying to emphasize is compression and tension and shear, and get away from bending and torsion.
So if you have this on a PC, you can look at each one of these to see what happens when you drag that slider across, or either less or more force. John? So kids get to see what we're talking about, each of those individual types of forces. And then some amplification of that in terms of the definitions. Some discussion of some materials are stronger in compression, tension, shear than in the torque or twisting motions. And bridge designs have to take into account the ability to maximize the strength of the structure in terms of compression, tension, and shear, and minimize the effects of torsion and bending forces. And I think we have a great video a little bit later. How many of you have seen the video of the Tacoma Narrows Bridge, which is a pretty famous engineering failure? We'll show that a little bit later. 4 basic types of bridges, from the simplest to perhaps the most complex. Simplest being just a beam bridge, like you see up here with the board and the chairs. A truss bridge, which is a beam bridge, can also be a truss bridge, a beam supported by a truss. Cantilevered bridge is a form of a truss bridge. Then arched bridges and suspension bridges, bridges similar to the Golden Gate Bridge, the suspension bridge. You can have two forms of that, one where the cables are actually suspended, and another called a cable stayed bridge, where cables are tied from the very top of support and anchored on the bridge itself. We'll show you examples of those as well. Here are a couple of examples of beam bridges. Is there a pointer on this?
The red button.
What's that? The top? Ah, I got it. So this is the simplest kind. This is just a log across a stream, probably the oldest form of bridge. Here's another example of a beam bridge. You can see this is a steel reinforced beam going across the stream. It looks like this one's anchored maybe at 2 or 3 points, one here, one here, one here. And that's the way most modern beam bridges are built, with box steel girders. Typically, something less than 250 feet for a beam bridge. Here you can see the forces that act on a beam bridge. You have the two supports, and of course, in our example here, we have all the weight in the middle, and the top of the bridge, you can see the forces are compression forces, and on the bottom of the beam, the forces act the other way and are in tension. Are you going to sit on this? You want me to sit on?
Very simple demonstration you can do with the kids. This is a 4x1 plane. And the question is, okay, if we put it that way, we've got these weights. We put those on. It flexes, if I have more weight, it's going to break. But if I put it like that, it doesn't flex anything like. Okay, you're all science teachers. What is happening? Why does it flex more this way than this way? What is the physics behind that? It's very simple physics.
The weight is distributed over.
Yeah, but what's happening?
That much of the billboard is carrying the weight as opposed to that much? Okay, wrong.
Look at that diagram.
You've got greater tension and tension and what's the other one? Compression in this amount of height than in this amount of height.
Can you go on one slide? I think it's okay. Basic. What it is couples, moments and couples. What Tom showed you before was when you push down in there, you get a compression force one way, and in the bottom, you get a tension force the other way. Okay? In the middle, you don't get anything. If you mentally visualize, I think pen is very good, mentally visualize connection, a couple pivoted in the middle between the two, the compression force is pushing that way, the tension force is pushing this way. So one is emphasizing the other. It's a couple. When you put it this way it's a short couple. When you put it this way, it's a long couple. So the deflection this way is going to be way less than it is that way because you can carry the load much more easily. Why that becomes important is, if you jump on, it leads to the I-beam. Because in the I-beam, since there's no forces, in the middle, you don't need the material there. Where you need the material is in the top and bottom. As in the I-beam, that's why they make it that way. So these two things here, this piece of furring strip bends as much as this I-beam like made up in thin wood. You put them on there and then push on it. And you feel the relative weights. This is much heavier than this. In fact, this is much stronger because I've got way more material up there than I have in there.